Welcome back to Click Future, where your future is a click away. This is the 6th episode in our Quantum Horizon series, where we explore the fascinating intersections of AI, quantum computing, and space achievements. What if you could detect a single molecule in a vast solution, or measure gravity so precisely you could see what's hidden underground, or detect the faintest signals from deep space? Today, we're exploring quantum sensing, a revolutionary technology that harnesses the strange properties of quantum mechanics to achieve unprecedented levels of precision in measurement. From transforming medical diagnosis to revolutionizing space exploration to mapping what lies beneath our feet, quantum sensors are poised to transform dozens of fields with their extraordinary capabilities. As Richard Feynman famously observed, there's plenty of room at the bottom. Quantum sensing takes us to that bottom, the very limits of what can be measured in our universe. To understand why quantum sensing is so revolutionary, we first need to understand the fundamental limits of classical sensing technologies. Classical sensors are ultimately limited by noise, random fluctuations that obscure the signal we're trying to measure. This noise comes from various sources, including thermal vibrations and the discrete nature of matter and energy. Quantum sensors exploit two key quantum properties, superposition and entanglement, to achieve sensitivities beyond classical limits. Superposition allows quantum systems to exist in multiple states simultaneously. By preparing a sensor in a superposition state, it can be exquisitely sensitive to tiny perturbations that would be lost in the noise for classical sensors. Entanglement, which we explored in our previous episode, allows quantum systems to be correlated in ways impossible for classical systems. This enables quantum sensors to reduce noise dramatically through what's called quantum squeezing. The result? Quantum sensors can approach the fundamental limits imposed by the Heisenberg uncertainty principle, the ultimate precision allowed by the laws of physics. Quantum sensors don't just offer incremental improvements, they can be orders of magnitude more sensitive than their classical counterparts. We're talking about measurement capabilities that were simply impossible before. One of the most promising applications of quantum sensing is in medicine, where more precise measurements can lead to earlier diagnosis and better treatment. Magnetic resonance imaging, or MRI, is already a powerful diagnostic tool, but quantum-enhanced MRI could dramatically improve resolution, potentially allowing doctors to see individual molecules within cells. Quantum magnetometers, which measure magnetic fields with unprecedented precision, can detect the tiniest magnetic fields produced by single molecules. This could revolutionize how we detect biomarkers for diseases like cancer, Alzheimer's, and Parkinson's. Researchers at Harvard have developed quantum diamond biosensors that can detect individual proteins and even monitor the electrical activity of single cells. These sensors use nitrogen vacancy centers in diamond, quantum defects that are exquisitely sensitive to magnetic fields. In 2024, a team at MIT demonstrated a quantum sensor that could detect specific cancer biomarkers at concentrations 1,000 times lower than conventional tests. This could enable cancer screening years before symptoms appear, when treatment is most effective. Quantum sensing could transform medicine from reactive to truly preventative. When we can detect diseases at their earliest stages, or even before they fully develop, we can intervene much more effectively. Quantum sensors are also being developed to monitor brain activity with unprecedented precision. These could help us better understand neurological disorders and potentially lead to more effective treatments for conditions like epilepsy, depression, and Alzheimer's. Space exploration presents unique measurement challenges that quantum sensors are uniquely positioned to address. In 2015, the LIGO Observatory made history by detecting gravitational waves, ripples in space-time caused by violent cosmic events. LIGO is already being upgraded with quantum squeezing technology to enhance its sensitivity. Future space-based gravitational wave observatories like LISA, Laser Interferometer Space Antenna, will incorporate quantum sensing to detect lower-frequency gravitational waves, potentially allowing us to observe the very early universe and better understand dark matter and dark energy. Quantum accelerometers and gyroscopes could revolutionize spacecraft navigation. Unlike current systems that drift over time and require regular corrections from Earth, quantum inertial sensors could maintain precise positioning for months or years without external reference. This would be crucial for deep space missions where communication delays make Earth-based navigation corrections impractical. A spacecraft using quantum navigation could autonomously navigate the outer solar system with unprecedented precision. Quantum-enhanced telescopes could dramatically improve our ability to detect faint signals from distant objects. By using entangled photons and quantum detection techniques, astronomers could potentially image exoplanets in unprecedented detail, perhaps even detecting biosignatures that would indicate alien life. Quantum sensing will be as revolutionary for space exploration as the telescope was for astronomy. We'll be able to see farther, measure more precisely, and detect phenomena that are currently invisible to us. Here on Earth, quantum gravity sensors are poised to transform how we understand what lies beneath our feet. Quantum gravity sensors use clouds of ultra-cold atoms in superposition states to measure tiny variations in gravitational fields. These variations can reveal underground structures that are invisible to other sensing technologies. In civil engineering, quantum gravity sensors could detect sinkholes, buried infrastructure, and archaeological remains without digging. In 2024, a UK company demonstrated a quantum gravity sensor that could detect a tunnel 10 meters underground from the surface, something impossible with conventional technologies. For resource exploration, these sensors could revolutionize how we find minerals, groundwater, and fossil fuels, making the process more efficient and less environmentally disruptive. In climate science, quantum gravity sensors deployed on satellites can measure changes in Earth's water distribution with unprecedented precision, tracking groundwater depletion, ice sheet mass, and sea level changes, crucial data for understanding and addressing climate change. The first precise measurements of Earth's gravity were made by Henry Cavendish in 1798 using a torsion balance. Today's quantum gravity sensors are millions of times more sensitive, yet compact enough to be deployed in the field or even in orbit. Quantum gravity sensors give us a new way of seeing inside the Earth. It's like having X-ray vision for geology, allowing us to map what's underground without disturbing it. As with any powerful technology, quantum sensing raises important ethical questions, particularly around privacy and security. Quantum sensors could potentially detect conversations through walls by measuring the tiny vibrations they cause, track people by their unique magnetic signatures, or identify substances from a distance with unprecedented accuracy. Military applications are already being developed, including quantum radar systems that could detect stealth aircraft, submarine detection systems that could undermine nuclear deterrence, and ultra-precise navigation systems that work without GPS. Policymakers and ethicists are beginning to develop frameworks for responsible quantum sensing development and deployment. The challenge is balancing beneficial applications with potential misuse. Researchers are also working on privacy-preserving quantum sensing, technologies that can achieve high sensitivity for legitimate applications while incorporating technical safeguards against privacy violations. With quantum sensing, we're approaching the physical limits of what can be measured. This raises profound questions about privacy in a world where walls might no longer provide the protection we assume they do. Quantum sensing represents one of the most practical and near-term applications of quantum technology. While quantum computers are still developing, quantum sensors are already being deployed in real-world applications. In the coming decade, we can expect quantum sensors to become increasingly common in healthcare, space exploration, geology, climate science, and many other fields. The measurement precision they offer will enable discoveries and applications we can barely imagine today. As we continue to develop these technologies, we'll need to balance their extraordinary potential for good with careful consideration of their ethical implications. With responsible development, quantum sensing could help us better understand both our planet and our universe, while improving human health and well-being. If you found this exploration of quantum sensing fascinating, please hit that subscribe button to join us on this journey through the technological frontiers shaping our future. And leave a comment below. Which quantum sensing application do you think will have the biggest impact on society? In our next episode, we'll tackle a mind-bending question. Are we living in a simulation? And could quantum computers help us find out? Until then, this has been Click Future, where your future is a click away.